In the previous episodes, I proposed using tramway gearing to achieve low backlash for the floating bar mechanism. I will assemble the gearbox in this video and test whether the concept works. Hi, welcome to Slow Engineering. I'm David. I selected the tramway gearbox to reduce backlash and improve the precision control between the floating bar and the XY gantry on Voron 2.4. I designed a flex spine gear with 10 teeth and utilized EVA filaments to reduce its axial length. The weight generator incorporates bearings to ensure smoother contact with the interior of the flex spine gear. Additionally, 2 set screws are used to secure the weight generator at the required height on the stepper shaft. I have fixed the flex spine gear with the solid plate to transfer the torque to the gearbox output shaft using multiple screws around the surface. This ensures the EVA parts won't experience too much stress at certain fixing positions. I use a grinder to remove any EVA material stringing, ensuring clean teeth and a smooth interior of the flex spine gear. After attaching the solid plate to the flex spine gear, I insert the output shaft into the flex spine gear and secure it with 2 additional set screws. To grind a surface onto the shaft, I designed a fixture with a grinder. I placed the shaft into the fixtures and ground out the protruding parts to create a surface on the shaft. Squeeze the pre-assembled flex spine gear and put it onto the weight generator. Then cover the flex spine gear with the circular gear housing. The solid plate on the flex spine gear should be almost the same level as the cover. Push a bearing into the bearing housing and install it on the output shaft. Next, place a white plate with angle marks, which will be the door panel in the future. This white plate will show the accuracy of the gearbox test. And the final is another bearing with the housing to stack onto the white plate. These parts will be fastened and fixed by 4 long M3 screws. I use an ESP32 board with the TMC 2209 driver to boost the stepper motor. In the initial attempt, I encountered an issue with the flex spine gear being too stiff to rotate the weight generator. To address this, I reduced the thickness of the junctions to increase flexibility. However, these modifications impact the dimensions of the weight generator. It's important to note that the number of the teeth on the flex spine gear is proportional to its diameter, and its inner diameter influences the length of the weight generator. Ultimately, the weight generator is responsible for pushing the flex spine gear towards the outer circular gear for proper engagement. On the second attempt, the output shaft spun. I instructed the steppers to rotate for about 10 cycles and then reverse. With a 5:1 ratio, the output shaft should complete 2 cycles. The white plate with angle marks and a pointer on the shaft can indicate accuracy after several cycles. The test results indicated the tramway gear has low backlash and performs well in accuracy. However, the gear got stuck again the next day when I attempted to conduct a load test. Therefore, I had to revisit the design to identify the cause of the issue. Upon disassembling the gear, I discovered that the flex spine gear was deformed in an oval shape, corresponding to the shape of the weight generator. The flex spine gear did not revert to its original shape after being removed from the weight generator. However, after approximately half an hour, it gradually returned to its circular shape, indicating the EVA material is a viscoelastic material. Viscoelastic materials do not immediately recover their shape after removing a load, but eventually return to their original shape after the load is removed. I attempted to reduce further the junction thickness to create a more flexible flex spine gear that could better maintain its shape after prolonged periods of being stationary. I increased the inner diameter of the flex spine gear to make the junction thinner without altering the tool shape. This approach proved effectively until I reduced the junction thickness to 0.8 mm, which amounts to 2 lines in 3D printing. However, these thin junctions resulted in ratcheting movement. When the shaft spins, the solid teeth exhibit noticeable ratcheting movement compared to the flexible links between the teeth. I also devised a better assembly design for smoother movement during the junction thickness tests, adding a slight chamfer at the top of the flex spine gear input the contact. The flex spine gear deforms with the weight generator, causing the teeth on the flex spine gear to be non-parallel to the circular gear. I reconsidered the TPU material due to EVA's viscoelastic phenomenon, which makes it unsuitable for this application. I bought another 95A TPU filaments for testing, and the result is better. However, the TPU still exhibits some viscoelastic effects. At this times, it works without apparent ratcheting movement. The output shaft can return to its starting point after several turns and turn back, which means the accuracy test passes. In the last episodes, I calculate that the mechanism requires around 187.5 Nm of torque. Upon inspecting the manufacturer's torque diagram, I found that the steppers can deliver around 40 Nm at a lower speed. Using a 5:1 gearbox, we can achieve around 200 Nm or 20.4 kg-centimeters. I attempted to create 196.2 Nm of torque for the load test using a 1.25 kg plate with a 16 cm wood bar. However, the stepper initially skips steps. I then reduced the weight and attempted to lift a 500-gram water bottle, but the stepper still failed. For further testing the gearbox efficiency, I make an 8:1 ratio gear set, but it did not lift a water bottle as expected. I realized I forgot to apply lubricant to the gears, so I added some grease to the gearbox and tried again. Unfortunately, there wasn't much improvement. Please comment down below if you have any ideas why the gearbox isn't working correctly. Increasing the gearbox ratio might provide the needed torque, but also reduce efficiency. There may be better way to design the mechanisms for this application. I presented two options for raising the bar. The more feasible choice would involve timing belts and pulleys to achieve the 5:1 ratio for lifting the floating mechanism. The decisions to switch to timing belts reduction is reasonable due to the low efficiency of the Shrimp gearbox. As always, moving forward.